Hello everyone and welcome to the next video in the series. This is a technical skills video on the topic of the structure of rational numbers. And to begin, I would like to first talk about the two different interpretations of the horizontal line that we use to separate the top and the bottom, as in 3/4. This can be seen in two different ways. One is as a division of three things into four parts. Let me show you a diagram of what it is that I'm talking about. So here we have three things, and let's say 3 pies, and we want to divide the 3 pies between 4 people and give everybody an equal amount of pie. And if we go about working it out, we'll end up with this image. You notice that that the shaded part that's light blue, this is one piece. The orange pieces together form another piece, so the blue is given to one person, and the orange pieces are given to another person. And if you take a look, the orange pieces all together have the same amount as the blue part. In fact, if you take this orange piece and move it over here, it becomes pretty similar to what we have here. And the yellow is the third part, and the orange and the my apologies, green is the other part. So we have divided three things into 4 parts: 1, 2, 3, and 4. And that's one view of the notation that we use, the 3/4. This is seen as division of, again, 3 things into 4 parts. And in the context of division, we refer to the top number as the dividend and the bottom number as divisor. Now, a second way to view 3/4 is as a fraction of 1. So this one means that we are talking about 3/4 of 1 pie. And in this case, we divide 1 into 4 parts and take 3 parts. Let me make the quick correction here. We divide the pie into 4 parts and we take 3 parts. Let me show you what I'm talking about in a diagram on the right side. So now we take a 1, divide the 1 into 4 parts, and take 3 parts. And we end up with the shaded area that we have here. This is the amount that we are talking about. And you notice that that this is the same amount as the one that we had for one of the pieces here. If you take a look, try to keep this size in mind and then compare it to this size. It's the same amount. So basically, if you take 3 things and divide them into 4 parts, the answer will be 3/4 of 1. And in fact, it wouldn't be odd at all for us to write something like, let's say, 3, and then we put down over 4 is equal to, and we put down another 3 and a 4. And although it may look strange, but you actually can read this as, if you divide 3 things into 4 parts, you end up with 3/4 of 1. So there are these two interpretations of the division that you should always have in mind. Which one is the one that people are talking about? It very much depends on the context. Okay, so here we see 3/4 as a number, as the size, as a fraction of 1 that we arrive at after we do any kind of calculations that we have to do. Here we divide 1 into 4 parts and take 3 parts. In the context of a fraction, we refer to the top as the numerator and the bottom as the denominator. Okay, so now let's talk about the different kinds of fractions that we have. And we start with proper fractions. These are fractions where the size, the overall size, is less than 1. As an example of that, we have 1/4, which would be this kind of a size. Now you can draw it like this, or some people prefer to draw a pie chart and they put down this kind of a diagram. Divide 1 into 4 parts, take 1. But in the end, that's the amount that we take, the shaded amount. If you imagine this is a pie, the white areas have been eaten and only the shaded area remains. So that's what we have. That's what 1/4 is. And we can talk about 2/4. You notice that the size of 1/4 is less than 1 whole pi. For 2/4, same thing. We can view it as 2 pieces. Each one is 1/4. Or we can arrange them in pi form and end up with this amount, which is again less than 1 whole pi. We have now, as a third example, we have 3/4, which is this amount, 3 pieces. Each one is 1/4. We can arrange them in pi form and end up with this kind of a diagram as 3/4. And again, the totality that we come to in the end is less than 1. These are what we call proper fractions. If we go to one more piece and talk about, now by the way, one thing that you notice is that in proper fractions the top is always less than the bottom, because keep in mind the bottom says how many pieces a pie should be cut into, and if you cut a pie into 4 parts, you need at least 4 parts to make a 1, and so anything less than 4, 1, 2 or 3 will make the total size less than 1 whole pi, and that's a proper fraction. So that's a quick way to check whether you have a proper fraction or not. What you do is you compare the top and the bottom, and if the top is less than the bottom, then the fraction is proper. Okay, so the numerator is less than the denominator. Improper fractions are either equal to 1 or larger than 1. So if we now add one more piece and talk about 4/4, 4 pieces, each one is 1/4, then we end up with this amount, and we can arrange them in pi form to end up with pretty much a 1. We can view 4/4 as 1, and so 4/4 becomes an improper fraction. Improper fractions, as I mentioned, have their sizes. Their sizes are either greater than 1 or equal to 1. And we can follow the same pattern. We can talk about 5/4, and this time in pi form, we'll end up 4 of them will make 1 whole pi, and then we'll have 1 extra quarter. And we can see this as 1 plus a quarter. And there is a shorthand for this notation as well, by the way. We write it down as 1 and 1/4 in this manner. So when you see 1 and a quarter, and that's how you read it, by the way, 1 and a quarter, it actually means 1 plus 1/4, a 1 with an additional quarter. Okay, so 4/4 is 1, 5/4 is 1. We have 6/4 next, and this one, if we arrange these quarters in pi form, we'll end up with 1 whole pi and 2/4 extra. Now, of course, 2/4 can be reduced, but for now I won't bother with that. So this can be seen as 1 plus 2/4, and we usually have a shorthand for this as before, and we write it down as 1 and 2/4. And then we have other fractions like 7/4. This is also improper. If we try to make pies out of these pieces, we'll end up with 1 and 3/4, 1 plus 3/4, which is 1 and 3/4. We can talk about 8/4, and this time we end up with 2 whole pies, and so 8/4 is 2. 9/4, we end up with 2 whole pies and 1 extra pie, 1/4 extra, so we end up with 2 and 1/4. In all cases, for improper fractions, the numerator is either greater than or equal to the denominator in size. You notice again that, for example, if you have a 4 as your denominator, that means 1 pi is cut into 4 parts. So you need at least 4 pieces to make a 1. So if the top and the bottom are equal, you end up with 1 pi. That makes it improper because size can be equal to 1 for improper fractions. If the top is larger, then with 4 of them you can make 1 pi, and then with you will have extra pieces left, and so the size will be greater than 1. One thing I would like to mention is that in mixed number form, this is what we call a mixed number, by the way, because the notation is a mix of a natural number and also a rational number, and we call them mixed numbers. It's important to keep in mind that for mixed numbers, it's important that the fractional part should be proper. So in order for me to call this a mixed number, the fractional part must be proper. I would like to explain why. Let's take a look at this problem where we have 15 quarters which are arranged in pi form, but each one is shown as a quarter. So we have 4 in 1, and then 12, 13, 14, 15. And we can take 4 pieces here and change that to 1 whole pi. It's similar to taking 4 quarters and getting a loonie from it. So now we end up with 1, and the remainder will be 11 quarters. There are 8 here, and then 9, 10, 11. So we end up with 1 and 11 quarters. So we can write it down like this. We can take another 4 pieces and make a 1. So now we have 2. That's 2 whole pies. And there are 4 pieces here and 3 there for a total of 7 quarters. So 2 and 7 quarters. And we can take the last 4 here that can make a whole pie and talk about 3 and 3 quarters. My apologies. Well, that should have been a 3 quarters. My apologies for that. But my point is that in the end, this is what we call a mixed number, where you have made as many whole pies as you possibly can, and the remainder doesn't add up to 1 whole pie. And this is what we call an improper fraction, where everything is broken into pieces. The in-betweens, which are these two, they sometimes come up along the way when we do calculations, but by and large we don't name them. We don't care about them as much to name them. We usually name things when we want to refer back to them. And the 2 scenarios which are important to us are the case when everything is broken down into pieces, and we call them improper fractions, and the case when we have formed as many whole pies as we can, and the remainder, which is the fractional part, is less than 1, and that's why it's a proper fraction. And so it's again important to remember that the fractional part in a mixed number must be proper. We do not call 1 and 11 quarters a mixed number. It is a number, it does make sense, we can use it in calculations, but we do not refer to it as a mixed number. Okay, so with mixed notation, 2 and 1 quarter is shorthand for 2 plus 1 quarter. And by the way, on that note, if you're dealing with negative 2 and 1 quarter, that's a shorthand for negative 2 minus 1 quarter. It refers to the negative of the totality that you see here. So negative of 2 and 1 quarter all in one, and therefore it becomes negative 2, and then subtract another quarter from it. And as I just mentioned, the fractional part of a mixed number must be proper. Okay, now we should be able to go from improper fractions to mixed numbers and back. So if somebody gives me 2 and 1 quarter, I should be able to change it to 9 quarters, and vice versa. If somebody gives me 9 quarters, I should be able to change it to 2 and 1 quarter. Why? The reason is because improper fractions are easier to work with. For the most part, there are some exceptions when you add and subtract, but for the most part, in the majority of scenarios, including in all multiplications and divisions, improper fractions are much easier to work with. But mixed numbers have their advantages. They are easier to comprehend size-wise. So if somebody says I have 9 quarters, and somebody says I have $2 and 1 quarter, it's much easier for us to comprehend the size of $2 and 1 quarter compared to 9 quarters. And the larger the number becomes, the more difficult it becomes to understand how much we are talking about. Imagine if somebody tells you I have 890 quarters or 891 quarters. It would be much better if they give you as many dollars as they can possibly make from those quarters with any change that's left. That would be so many dollars and let's say 3 quarters. That would be much easier to understand and comprehend. So in order to put each of these to use, we draw on their advantages. For improper fractions, because they are easier to work with, what we do is we use them when we when we do calculations. So if a problem begins with mixed numbers, such as this problem, 2 and 3 quarters multiplied by 1.5. We would prefer to convert them to improper fractions, because again, improper fractions are much easier to multiply, And I'll show you how you convert them to improper fractions. But once you do that, you end up with 11 quarters times 3 halves. And these are much easier to multiply, and we end up with 33 eighths. Now, 33 eighths is pretty difficult to comprehend size-wise. So what we do now is switch back to the use of mixed numbers and put down 4 and 1/8. And that's much easier to understand size-wise. So initially, if we have mixed numbers, we convert to improper fractions. That tells you that you need to know how to go from mixed numbers to improper fractions. In the end, if your final answer is improper, then you should convert to a mixed number, so that the person who's looking at your report can tell what the size of the final answer is. Leaving it with 33 eighths is like leaving them hanging in the air. Okay, so how much are we talking about exactly here? And so that's the next topic for us. When we convert from an improper fraction to a mixed number. Let's say we have 9 quarters and we want to convert this to a mixed number. So 9 quarters, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Each one is a quarter, so we have 9 quarters. If we arrange them in pi form, we get this diagram. With 8 of them, we can make 2 pies, and then there will be 1 quarter extra. Now, in order to work out how to go from, so let me actually make this diagram a bit smaller. I'm going to remove the middle part and just put the top and the bottom. Okay, so this is what we have. Now, in order for us to know how to convert without using diagrams, of course, what we notice is that because with 4 of these, we can make 1 pi, and we have 9 in total, the question becomes, how many groups of 4 can we take out of 9? That will tell us how many whole pies we get. And is there any extra pieces left? These are the kinds of questions that long division answers. So basically, we divide 9 by 4 to find out how many groups of 4 fit into 9 pieces. And the answer to that is 2 of them. So we have 2 times 4, 8, and then we subtract to get 1. And so we can form 2 whole pies, and there will be a remainder of 1 quarter. Okay, so let's take a look at this again. Time going backwards, time going forwards. Okay, so how many 4s fit into 9? Again, the reason we do that is because we want to find out how many groups of 4 fit into 9. Every group of 4 will give us 1 pi. And in this case, we find that there are 2 groups of 4. So we can make 2 whole pies. And 2 groups of 4 translate into 8 quarters. And if we subtract, we'll be left with 1 quarter left. So the answer is 2 and 1 quarter. Please note where the numbers go. The quotient is the number of whole pies. The remainder is the bits and pieces that remain, 1 quarter. And so we can now write down 9 quarters is equal to 2 and 1 quarter. Going the other way, I'm going to use the same problem here. So this time, suppose that we have 2 and 1 quarter and we want to convert it back to 9 quarters. And in this case, what we'll do is, because this pie is cut into 4 pieces, we cut each of these into 4 pieces as well. As many pieces as this one is cut into. And if we do that, for each one we get 4 pieces. And because we have 2 pies, each one cut into 4 pieces, in total we get 8 pieces for the 2. And so we can multiply 4 by 2, that's 2 pies, each one getting cut into 4 pieces, for a total of 4 times 2, 8 pieces. And then we add the extra one that we have, and we get 9. And therefore the algorithm becomes, you multiply 4 by 2 to find out how many pieces the whole pies generate. Each one is cut into 4 parts, and we have 2 of them. 2 times 4, 8 pieces here, and then we add the 1 to find a total of 9 pieces. And that gives us 9 quarters back. So we have 4 times 2, 8, 8 plus 1, 9, and we get 9 quarters. The size of a piece, of course, doesn't change. A quarter stays a quarter in this case. And therefore, 2 and a quarter is 9 quarters. All right. And the last topic for this video on structure of rational numbers is on reduction. And the task of reduction is to reduce the sizes of the numerator and the denominator, but keep the overall size the same. In the previous video, I did make a comment about this, and let's go deeper into it now. So first of all, why reduce? The reason is because reduced fractions are much easier to comprehend. You compare 243 over 405, and its reduced form is 3/5. Who would argue that 3/5 is not easier to comprehend size-wise? So if somebody says, okay, after my calculations, you get 243 4/5 of a pi, you have no idea what they're talking about. But if they say 3/5 of the pi, it's very, very clear how much they are talking about. In addition to making the size more easier to understand, reduction is also used, as I mentioned, routinely in multiplication and division, as well as in parts of addition and subtraction. Okay, so now that we know why we need to reduce, let's talk about how to reduce. Okay, on the question of how we go about to reduce, the steps that I give you are probably the most efficient approach that you can have, and they are sort of easy. Again, it so much depends on how well you know your times table. That's the key in making working with fractions efficient. Without a good knowledge of the times table, what will happen is that the process will be slow. No matter what you try to do, whether you adopt a better algorithm or not, one that's not so good, still in both cases you have to spend so much time figuring out the results of your divisions that the task becomes frustrating. But in any case, the most efficient way probably to reduce a fraction is to start with the divisibility test by 10. And the reason that I mention I choose 10 first is because number one, it's so easy to divide by 10, you just cross out a 0. And number two, because 10 is a large number, it makes your numbers much smaller, much faster. Then following that, I recommend that you use any number that you can think of. By the way, the number doesn't have to be a prime. In case you can see that, for example, 8 goes into a fraction, let's say 16 over 24. 8 goes into both. And again, if your times table is decent, you would know that 8 goes into 16 twice and 8 goes into 24 3 times. So use 8 and finish the problem. There is no reason why you have to stick to primes. We only use primes when things get tough. But if you can see a number that goes in, by all means use it at any point in time. So from now on, if you can think of any number that you can use, then use it. I do recommend that you do this after 10. Because if you can divide by 10 and instead you opt for 2, it's not as good an approach. Division by 2 is more difficult than division by 10, and also 10 makes the numbers much smaller, much faster compared to, let's say, 2. Okay, following this, if you've used 2 and you cannot think of any numbers that you can use, and you're not quite sure if it's done or not, try divisibility test by 5, 2, 3. 5 first, again, because division by 5 is somewhat easy, and also 5 is the larger one of the 3, and it makes the size of the answer much smaller, much faster. Followed by 2, and then 3. By 2 first, because division by 2 is easier than division by 3. And the test for 2 is also easier than the test for 3. And if none of these work and you still are not sure whether you're done or not, then you do a process that's called prime factorization. In my approach, I highly recommend that you prime factorize either the top or the bottom. Not both. Most textbooks and teachers would tell you that you need to prime factorize both the top and the bottom and find commonalities. There is no need to do that. Prime factorization is somewhat time consuming, and some numbers are very difficult to prime factorize. And if let's say the numerator is easy to prime factorize and the denominator is difficult to prime factorize, you spend a lot of time doing both, when all you need to do is just the top, which is easier in the example that I just gave you. Okay, let's go through some examples as to how we reduce fractions with some easy ones, and then we'll pretty much have examples that take use of all of these steps. Problem number 1, 6/8, which we talked about before. So 10 doesn't work, and let's say, well, I can think of 2 right now, so let's use it. That's step number 2. We divide both the top and the bottom by 2, and we get 3/4. On that note, by the way, if you have a mixed number, the whole part doesn't get touched, because if you think about 6/8, we're talking about a pie that's cut into 8 pieces, and we take 6, and then we change that to 3/4. The 2 on the side says that you have 2 whole pies, and the 2 whole pies stay the same. It's only the one that's cut into 6/8 that we change to 3/4. So imagine 2 whole pies, and then a third one that's cut into 8 pieces, and you have 6 of those. That's the same as 2 whole pies, and the third one is cut into 4 pieces, and you have 3 of those. So the whole part doesn't change. And if a fraction is negative, now here we are talking about rational numbers, of course. Again, rationals are positive and negative fractions as well as 0. And so here the answer will be negative as well. So you reduce 6 and 8 in the usual way, but the answer is negative. Okay, next we have 49/56. And here is where the times table comes in. Again, if you know your times table well, you can just take a look at this and say that 7 goes in, and that it goes into the top 7 times, into the bottom 8 times. And we end up with 7/8. Okay, in this case, if I wanted to follow the algorithm, let's say it's a bit tough for me to work it out, and then I try 10, it doesn't work because neither one has a 0 at the end. I cannot think of any number that goes into both. Let's say my times table is not very good. I try 5, doesn't work because neither number ends in 0 or 5. 2 doesn't work, the top is not even. For 3, let's see, 4 plus 9 is 13, and 3 doesn't go into 13 evenly, so 3 doesn't work. And now we are at the step where we have to do prime factorization. But I would like to pose prime factorization in the context of even a more difficult problem, like 57/95. Even with a good knowledge of times table, this is not an easy one to prime factorize, to reduce. And so let's see how we go about using prime factorization on this problem. Now here 10 doesn't work. Let's say we've gone through the process. 10 doesn't work. I cannot really think of any number that goes into 57 and 95. 5 works for the bottom, not the top. 2 doesn't work for either one. As far as 3 goes, 5 and 7, 12. 5 plus 7 is 12, so 3 works for the top. 9 plus 5 is 14. 3 doesn't work for the bottom. And I'm not quite sure if this is done. I have this kind of feeling that with numbers it can be tricky, by the way. You might take a look at 2 numbers and say there is no way this can be reduced, and then you'll find that they can. Even if you have experience, it's tough with some numbers to tell. So for example, who would be able to just glance at 57 and say, yeah, guaranteed 3 goes in? It's sort of like tough to tell. So anyways, now we have to prime factorize. And when I take a look at the top and the bottom and I try to see which one to prime factorize, so long as you can think of any number that can go to the top, then the top is a good one to start prime factorizing. Or so long as you see something that goes into the bottom, then you may want to start with that one. So in this case, both of them seem to be reasonably easy. I can see that 3 goes into the top because 5 plus 7 is 12, and I can see that 5 goes into the bottom. So I can pick either one, and I choose to go with, of course, in this case, because both seem to be easy, I go with the smaller one. And what I do is, here are the primes, and I put 57 and put a line on the side. Now we are going to use primes only and find out what number goes into 57. If any prime goes into 57, we divide 57 by it, starting with 2. And this is not even, and therefore 2 doesn't go in. Then comes 3. 5 plus 7 is 12, and 3 does go into 12. So 57 is divisible by 3. And so we write 3 down. And we divide 57 by 3, and that gives us 19. Now, because 19 is a prime, only 19 goes into 19. Before we move on, before we continue though, here we've got one prime. So when we say prime factorize the numerator or the denominator and test the primes that show up, right now 3 showed up. This is a prime that showed up. And we're going to try 3 and see if we can reduce the fraction with using 3. We know it goes into 57 because we just divided by 3. The question is, does it go into 95? And the answer is no, because 95, 9 plus 5 is 14. 3 doesn't go in. So we move on with prime factorization. Now 19, 2 doesn't go in, 3 doesn't go in. In fact, if you know that 19 is a prime, then only 19 goes into itself. And therefore we write down 19, divide and get 1. Now another prime shows up, 19. And we know that it goes into 57 because we are dividing and we find that 19 is part of 57. The question is, does it go into 95? And the answer is yes. If you actually try it, you'll find that 19 does go into 95. And in fact, it goes in 5 times. And so we reduce 57 over 95 to 3/5. And look at how many divisions we had to do. We did 1 division here, 2 divisions. Well, I wouldn't even call that a division. Like 19 divided by 19, 1 is not like you have to do long division for it. So we did 1 division here, and then we did 1 division, 95 divided by 19. 2 divisions, and we were done. This would have been a very, very time-consuming problem. If we used brute force, we were looking at, in the worst case scenario, something like about maybe 38 divisions. In the best case scenario, something like 20 divisions. We did it with 2 divisions. Okay, everyone, just before we finish the talk, here we have 6/8 and here we have 3/4, and just to show you that why reduction works again, as in the previous video, when you go from 6 to 3, you take half as many pieces. Instead of 6 of them, you take 3 of them. In going from 8 to 4, the size of each piece doubles. You take half as many pieces, each one is twice the size, and they cancel each other's effect. You end up with the same amount. If you divide the top and the bottom by, let's say, 3, then that means that when you divide the top by 3, you're taking 1/3 as many pieces. And when you divide the bottom by 3, the size of each piece becomes 3 times larger, and the 2 of them cancel out each other's effects. And also, I would like to make a note as to how you go about actually writing things down as you reduce a fraction. So going back to the same problems that we had, let's say to reduce 6/8, once you notice that 2 works, you cross out 6, divide by 2 to get 3, and you cross out 8 and divide by 2 to get 4, and the answer is 3/4. For 49 over 56, if your times table is good, you can see that 7 goes in right away. You cross out the top, 49, 7 goes into 49 7 times, and it goes into 56 8 times, and we get 7/8. So that's how you would do the work by hand. Okay, everyone, that's the end of the video on the structure of rational numbers, and in the next video I will be talking about the formal reading of rational numbers, followed by order, addition, subtraction, and then multiplication and division. There will be one more, I believe, yes, on expressions. Take care, everyone. Thanks again for watching, and I'll see you in the next video.